Hi guys, and welcome to my new subscribers and old subscribers, and welcome to anyone who's not subscribed yet and is watching. Please remember to subscribe to this video. You can do it now right down at the bottom, or wait till the end of the video and click on the little button. It really does mean a lot, the subscribers. And also a big thank you to, I think it's Memalaus, who has joined Ploppy as a Patreon pledger. Your shout out that you requested will be coming in a future video shortly, so keep tuned, stay tuned. But today we're going to look at strong and weak acids in the topic 4, chemical changes, and we're going to be building on the previous lessons work on the pH scale and neutralization. So we're going to be looking at the difference between strong and weak acids in terms of something called ionization, which you may also hear described as dissociation. We're going to look at some examples of some strong and weak acids because the exam board requires you to know about 3 of each. And we're going to look how the concentration of hydrogen ions changes with pH. So we looked at that last lesson. We looked at the fact that hydrogen ions are released by acids in aqueous solutions, so in other words when they're dissolved in water. So we're going to have a look at that and what that means for pH. Now, get your brains working. Here are 5 starter questions. You can put the video on pause and work yourself through these and see if you can answer them. So put the video on pause now, and then you can start to play it again when you have got your answers. So here they come. Acids release hydrogen ions or H+ ions in solution. Alkalis release OH- in solution. Sulfuric acid, the chemical formula H2SO4, that's important, you will be expected to know that, is an example of a strong acid, not just an acid but a strong acid, and again you may already know that from previous learning. HCl is the chemical formula for hydrochloric acid, and again it is also a strong acid, and it's probably the one you use most of all in school. NaOH is sodium hydroxide, and that is a strong alkali, and again that's probably the alkali you use most often in school. So they're the quick answers. Thumbs up and leave a comment if you got all 5 of those right. Little recap then. So acids produce hydrogen ions, H+ ions in solution. So they've lost an electron, they've got a positive charge when they dissolve in water. Alkalis, they contain hydroxide ions, OH, so oxygen and hydrogen, this time with a -1 charge. The pH scale is from 0 to 14, and it's a measure of the concentration of these hydrogen ions here. And then a new little bit of learning, the splitting of the acids and alkalis into their ions, the H+ and the OH-, or the hydrogen ion and the hydroxide ion, is called ionization or dissociation. Okay, dissociation because they're dissociating apart from each other, they're splitting apart, or ionization because they're making ions. Okay, so you are expected to know this little bit. It's quite simple. Now, if we have a look at the ionization or the dissociation of a generic acid, so this could be any acid, it doesn't matter what acid it is, it happens in the same way. If we take our generic acid, HA, and we can see it's aqueous, so dissolved in water. H is a hydrogen, A is everything else that might be attached to that hydrogen. So for example, we'll look at hydrochloric acid next, HCl, so the A would be the Cl. Sulfuric acid, which we saw above, is H2SO4, so we'd have H2SO4 for the A part. We know it's going to dissolve and it's going to release, if it's an acid, what type of ion? Yeah, a hydrogen ion, a H+. And then the other part that's going to be left behind is the A, and that will have the minus charge on it. Okay, because it's the charges on these 2 ions have to add up to 0 because this molecule has no charge overall. If it had a charge, you would see the charge written above it. So it splits apart into H+ and A-, so 1+, 1-, so you can now imagine it's 1 plus -1, 0 overall charge. So we'll have a look at what this looks like, for hydrochloric acid. So hydrochloric acid is HCl. Now have a little think, what's it going to break down into? What do all acids break down into? There's my little clue. So all acids break down to make H+, and then we're also going to be left with then the Cl-, which is the other part, the A that's been left behind. Okay, so it's just a substitution. So any generic acid, HA, makes H plus A minus. We just swap the bits here. So H, and everything left over becomes the A with a negative charge on it. If we add two H's, again we just make a big 2 in front of the H here. So not H2, because that would suggest that it's bonded together, but a big 2 in front of it, 2H. Okay, have a look at these ones. We've got sulfuric acid, nitric acid, and methanoic acid, and the methanoic acid is slightly wrong, and I'm just going to alter that and carry on with the video. So there we go. Methanoic acid is only CHOOH. So put the video on pause, give it a go, and see if you can work out what these would dissociate into. Look at these two examples. Remember, we're going to make a H plus and an A minus. So put the video on pause, give yourself a little go of working it out. Do try it, even if you're not sure, give it a go. That's a really good way of learning and testing your brain, pushing your brain to help you remember it better. Alright, answers then. Sulfuric acid, H2SO4. It's aqueous. Remember the state symbols? It breaks down into two hydrogens, or two hydrogen ions, H+, because we've got two hydrogens here, H2, so we get 2H. As I said, we don't have the H2 there, because that suggests they're chemically joined together. These aren't, they're floating around separate. Plus SO4, 2-, and if you remember what I said earlier, the charges have got to balance out. So we've got two lots of 1, so we've got 1 plus 1 plus 1, so that's 2, plus -2. So 2 plus -2 is 0 charge altogether. Nitric acid, nice and easy. HNO3, aqueous, breaks down into H+, aqueous, plus NO3 minus, aqueous. So we just split it apart. And this is the hydrogen that we're concerned about here in the methanoic acid, which is why I've highlighted it in bold. So we take our CHOOH, and turn it into H plus, aqueous, plus CH, and that should be CH, no 2 there, just CHOO minus. Okay, how did you get on with those? Everyone okay? Leave a comment below if you're unsure, or if you've got them all right. Again, leave us a comment, let us know. So, strong and weak acids. So, sulfuric acid is obviously a strong acid. We know that from working in labs, and it can also make, as we've just seen there, 2 hydrogen ions. So it's obviously a strong acid if it can make 2 hydrogen ions. But the next question is hydrochloric acid and methanoic acid, which we just had a look at, methanoic acid on the previous slide, both dissociate to give 1 hydrogen ion. However, hydrochloric acid is a strong acid, pH of 1. Methanoic, weak acid, pH of 4. Why do we have that difference? So, let's have a look at this now. Here's the dissociation of an acid, a generic acid. I don't know why the Q's have kind of disappeared there, apologies about that. So for a strong acid, what happens is the acid fully dissociates into H plus and A minus. So all of the acid breaks down. So we have, when we dissolve a strong acid in water, almost all of this breaks apart, ionizes, and makes the H plus and A minus. So we get 1% HA and 99% H plus and A minus. For a weak acid, it only partially dissociates or ionizes. So you end up with like 99% HA and only 1% H plus and A minus. So we get much less H plus in the solution, and that means it's much less acidic. This is what I mean about the dissociation. So if we take a strong acid, so we've got our strong acid, and example is hydrochloric acid, HCl. and we make it aqueous, it dissociates or ionizes into hydrogen ions plus chloride ions, both aqueous. Now in a strong acid, we're left with a ratio of like 1 to 99, for example. So we get 99% makes this stuff here. For a weak acid, like methanoic acid, which has the formula CH OOH, again aqueous, we're dissolving it in water. This time, this double-headed arrow suggesting it can go both ways, we're going to make H plus again, but we're also going to make the CH OO minus aqueous. Choo! This time it's the other way around. We end up with 99% of this. Very little of this breaks down. We end up with only 1% of this. These aren't real numbers, these are just numbers to demonstrate the principle. So we end up with a strong acid, full or almost full dissociation or ionization. With a weak acid, very little ionization. So that is the difference. This is why we have a difference in pH between our hydrochloric acid and our methanoic acid, because our hydrochloric acid makes a lot of hydrogen ions in the solution. The methanoic acid doesn't make a lot of the hydrogen ions in solution. And what we're going to see coming up as well is we're going to see me writing H plus in a little square brackets, and that means the concentration of those hydrogen ions. It's a convention in chemistry that if you write a chemical species, so it could be an element or a compound or anything like that, inside square brackets, you mean you're talking about the concentration of that thing. Okay, now before we go into the nitty-gritty about the concentration of the hydrogen ions and what that means for pH, we're going to have a look at some examples of some strong and weak acids that the exam board specifies that you need to know. So for the strong acids, you need to know that hydrochloric acid is a strong acid. You need to know sulfuric acid is a strong acid. You need to know nitric acid is a strong acid. Even better if you can remember the formulas for those. For weak acids, ethanoic acid, which essentially is the acid in vinegar, citric acid, which is essentially, well, it is the acid inside citric fruits, hence the name, and then carbonic acid, which is often formed by carbon dioxide dissolving in water. You don't need to know the chemical formulas for the weak acids, but for the strong acids, yes, learn those three. Now, pH and what it means in terms of the concentration of hydrogen ions. Remember, the square brackets means concentration of whatever chemical is inside the square brackets. So, pH is a measure of concentration of hydrogen ions in solution. It's something called an inverse logarithmic scale. Don't worry about that too much if you find those words confusing, not sure what they mean. We're going to go through that in a second. But the basics of it, it means that the lower the pH, the lower the number of the pH, so the more towards 0 it gets, like 0 and 1, 2, that means the higher the concentration of hydrogen ions, which is why strong acid has got a pH of 1, because it's got a high concentration of hydrogen ions. What it means by the logarithmic part is a solution with a pH of 6 has 10 times greater the concentration of hydrogen ions than a solution with pH 7. So every time you go down 1 pH, you get 10 times greater concentration of hydrogen ions. So every time you go up a pH scale, so going from 6 to 7, you get a reduction in your hydrogen ion concentration by 10 times. And we'll have a look at what that means now. So, it's a very good way, the pH scale. The reason why we use pH and we don't use a concentration of hydrogen ions is because the concentration of hydrogen ions is a very small number. So it's a really useful conversion tool to make things nice and simple for us when we are looking at the pHs and we're looking at acids and alkalis and how strong they are. So here's a little table to explain this, and you don't need to learn this table, it's just a very useful way of having a look at the fact that pH changes depending on the hydrogen ion concentration, and you are expected to know that how the hydrogen ion concentration changes. So pH is at the top, 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 14. And then we have our concentration of hydrogen ions in moles per decimeter cubed on the bottom rank of the table. Now we can see at a pH of 0, we have 1 mole of hydrogen ions per decimeter cubed of solution. At pH of 1, we've reduced that concentration by 10 times. We've divided the concentration by 10. So it's now 10 to the power of minus 1, or 0.1. pH of 2, we've got 10 to the minus 2, or 0.02 moles of hydrogen ions per decimeter cubed. 3, 10 to the minus 3, or 0.001 moles per decimeter cubed, and so on. So you can see why we use pH and not the concentration of hydrogen ions. If we had to write out the concentration of hydrogen ions, so say we measured that something was a pH of 12, and we had to write out, oh, its concentration of hydrogen ions is 10 to the minus 12, or even worse, 0.00000000001. That would be really, really, really painful to do. So the pH is a way of converting these numbers into a scale that makes much more sense for us, and you can see, can't you, here, that essentially the pH is the inverse, so we're taking away the negative of the power for the hydrogen ion concentrations. Okay, so high value of hydrogen ion concentration, sorry, a low value of hydrogen ion concentration down this end, so 10 to the minus 14, that's a low concentration, matches with a high pH, inverse. High value of hydrogen ion concentration, so for example 1, matches with a low value of pH. And a change of pH by 1 changes the concentration of hydrogen ions by 10 times. So going from 1 to 2 is a 10 times change. Going from 1 to 3 is a 10 times 10 change. So 100 times change. So something that an acid that's pH of 3, the concentration of hydrogen ions is 100 times less than something with a pH of 1. Okay, now we're going to look at concentration and pH in a bit more detail, what these things mean. So diluting an acid will lower its pH because you reduce the concentration of hydrogen ions in the solution. That makes sense, doesn't it? If you take an acid, if I give you a bottle of acid and you dilute it, you reduce the concentration of hydrogen ions in that solution, so you will lower the pH of that solution. Good example of this is at school we get bottles of concentrated acid delivered to us, so very, very strong acid. Obviously, if we're giving that out to pupils, especially in the lower years, that's potentially dangerous and hazardous. And even I'm not a massive fan of working with concentrated acids, so we dilute them first. So we buy the bottles of concentrated acid and we dilute them to a safe level. It lowers it, or it reduces, or increases, I should say, the pH. It moves it from 0.5 up to about 1.2. Now, something that is dilute, if you don't know this is a little bit of information that you probably should know. So something that's dilute has a little of that substance in a given volume of solution. For example, if I have a dilute acid or dilute squash, there is only a little bit of squash or a little bit of acid in the whole vessel that I'm containing it in. Something that's concentrated has got a lot of that substance in a given volume. So your orange squash comes in a concentrate. That is very, very concentrated orange juice, and we have to dilute it. Okay, and obviously we dilute it by adding more water. Now for the summary. So, what we've covered today. Strong acids ionize or dissociate completely in solution to release H+ ions, hydrogen ions. Weak acids dissociate only partially in solution. pH is a measure of the hydrogen ion concentration, and every time the pH decreases by 1, the hydrogen ion concentration goes up by 10 times. Okay, 10 times. And the inverse is obviously true. Every time the pH increases by 1, the hydrogen ion concentration goes down by 10 times. Okay guys, I hope you enjoyed the video, you found it useful and you have learnt something. Please remember, if you have not done so, to like and subscribe the video. Please share the video as well with anyone who you think might find it interesting or useful. It's great to see so much engagement with the videos. You know, it really gives me the enthusiasm to carry on making them. I'm trying a new mic today as well, new microphone, so let me know if you think the sound quality is worse or better, or in fact just the same as previous videos. And if you've got any comments, any suggestions, please leave them down below. Be delighted to read those, and I look forward to seeing you soon. Okay, take care guys, and stay healthy. Bye bye.